Hey guys, we're back and we're doing section 2 of chapter 4. We're talking about graphing exponential decay functions, and we went over that today in our activity with our Desmos activity where we explored exponential growth and then what happens when those numbers decrease, and we call that exponential decay. So today students will be able to, graph and use exponential functions to model depreciation, and depreciation is value that gets smaller and smaller over time. So a couple of things we need to know is our key vocabulary words. The first one is the exponential decay functions. And the exponential decay function is in the form of y equals some value of a times b to the x, where we know a is something that's greater than 0. And the b value, however, is something between 0 and 1, meaning it's a fraction. Okay, it's smaller than 1, but it's not negative. And this is also called the decay factor, is b, which tells you how fast something is going to decay or get smaller. So let's talk about the parent function for the exponential decay. So we know this is our exponential function. When the b value is a fraction, that's when we call it decay, meaning it's going to get smaller. Every exponential function goes through this point 0, 1. And then the next point that we're going to plug in is when x is 1, the value is 1, whatever the value of b is. And then we know it gets flat as it goes. And so that means that the x-axis is an asymptote. Because it never touches that x-axis. It gets smaller and smaller and smaller and smaller and closer to 0 as x gets bigger, but it never actually crosses that value. Okay? And the domain of the function b to the x power is all reals. And the range means where are the y values? We know that it has to be positive, so it's going to be y is greater than 0. So how would we graph y equals 1/2 to the x? So step 1 is we're going to make a chart. And the chart we're going to use is the same values that we've been using for our other exponential functions, -1, 0, 1, and 2. And we're going to plug it in right here into that function. So this is 1/2 to the x power, 1/2 to the x power, 1/2 to the x power, 1/2 to the x power. And what we're going to do is we're going to plug in those values, -1, 0, 1, and 2. And now we're going to solve these. I know anything to a negative exponent, the negative exponent becomes the 1 over. And this is 1/2 to the 1 power. So 1/2 to the 1 is just a half on the bottom. And 1 divided by a half is the same as dividing by the reciprocal of 1/2, which is 2. Anything to the 0 power is 1. 1/2 to the 1 power is a half. And 1/2 to the 2 power is 1/2 times itself, which is 1/4. So now that we have those values, we're going to plot the points. So the first point we're going to plot is -1, 2. And here's my graph. So here's when x is -1, and that point right here is 2. And then we look at 0, 1. So over 0, up 1. And then 1, 1/2. So here's where x equals 1, up 1/2. And then over x equals 2, y is up 1/4, which looks like that. And then step 3, just like before, we're going to connect the dots with a curve, a smooth curve. So it's going to look like this. And remember, it's going to get closer and closer to the x-axis, but not touch it. And then this is going to go up this way. So a smooth curve. And that's how we're going to graph the function. So how would we graph this one? So a couple of things here. Again, step one, let's make a table. Let's choose -1, 0, 1, and 2. And here we go, we get 2 times 1/4 to the -1, 2 times 1/4 to the 0, 2 times 1/4 to the 1, and 2, that looks like a 3, but it's a 2, times 1/4 to the 2. Oh boy, I didn't write that very good, did I? To the 2 power. So this right here, we do this first. 1 over 1/4 is really just 4. And when I multiply that by 2, that's 2 times 8, or 2 times 4, I should say, is 8. 1/4 to the 0 is 1. 2 times 1 is 2. 2 times 1/4 to the 1 is 1/4, which is 1/2. And 2 times 1/4 squared is 1/16. So this is 2/16, which is really 1/8. So step 2 is we're going to plot the points. And I'm going to change our graph paper for just a second so I can get some better points in here. All right, here's our graph where we've got -1, 8, 1, 2, 3, 4, 5, 6, 7, 8. Here's our point, 0, 2, 1, 1/2, and 2, 1/8. So we see this pretty, it's a lot more pronounced, but this is a curve that gets a little bit steeper. And there it is. And then step 3 was to connect those dots. The last one is, in order to do this, you can do one of two ways. You can still do your chart, or we can look at the parent graph. So step 1 is we can graph the parent function, and then we can look at the different transformations, how it changes, and graph it from there. So remember that our parent function is going to be y equals 1/2 to the x power, which when I graph that really quickly, I know 1/2 to the 0 power is 1, 1/2 to the 1 power is 1/2, and so on. So our parent function is going to look something like this. Okay, so this is our parent function. Looking at our function of y here, we see there's a 3, there's a +1 on the x, and there's a -2. So remember that this 3 in front gives us a vertical stretch by a factor of 3, which means everything's going to get 3 times taller. This is a vertical translation or shift down 2. And then this here attached to the x is, remember, when something's inside or attached to the x, that's the horizontal change. It's a translation. Remember, this is funky town, so when you see +1, it's really going to the left 1. So now we're going to take every point that we had on our parent function and do this. We're going to stretch by a factor of 3, go to the left 1, and down 2. So first thing we're going to do is we're going to find the height of each point. So here's our point right here at 2. So if I stretch it by a factor of 3, that just means I'm going to multiply it by 3. So 2 times 3 is 6. So we're going to stretch that to 6. So 2, 4, 6. Here's my new point. And then we're going to go left 1, down 2. So here we go, left 1 and down 2. So that's my new point after the stretch and translations. So here we go. I'm going to make that in a littler dot. Here's the next one. Here's my next point. I'm going to stretch it by a factor of 3. So right now the height is 1, so I'm going to stretch it to a height of 3, and then go left 1, down 2. That's what it looks like. And then lastly, here's this right here at 1/2. We're going to multiply it by a factor of 3. So 1/2 times 3 is 3/2, which is 1 1/2. To the left, 1, and we're going to go down 2. So that is my point, and I'm going to connect all of my dots in a nice, smooth line. And there's my function, my graph. So again, we graphed the parent function, and then step 2, we analyze the transformations for each point. Okay. So that brings us to an exponential decay model. So this is what happens in real life. So when we have a real life example of exponential models, just like we did before, we're going to do this, okay? Where A is the starting amount or initial amount. This minus here is how you know it's decay, because it's getting smaller. So when you see the minus there, that's how you know that it's for sure a decay model. This R right here is your rate percentage, but it's got to be in a decimal. And lastly, this is your T, which is your time unit. Okay. So that's all we got for our notes today. I will see you in class.